Welcome everyone. This is fourth video in estimation theory. In this video, I will talk about maximum likelihood estimator. This is a very important topic, so make sure that you watch the video till the very end because I have chosen three important problems to discuss in this video. But before I take any problem, let us quickly talk about the basics of it. In case if you are new to the channel, you should subscribe the channel as well because it will help you to get good quality video content. So the method of maximum likelihood estimation. The most general method of estimation known is the method of maximum likelihood estimator. So this is one of the most general method of estimation, and which was initially formulated by C.F. Gauss, but as a general method of estimation was first introduced by R.A. Fisher. So if it is asked that who introduced as a general method of estimation, then I will answer it as R.A. Fisher because he was someone who provided a general method of estimation using this technique. So before we talk about the problems, I want to talk about something known as likelihood function. So what is likelihood function? So for any sample which is given like x1 to xn, suppose we want to write the likelihood function L. So likelihood function L for the sample x1, x2, xn is defined like this, where f of x theta is the population density function. Right, we have talked about this kind of function in sufficiency video also, but just for the sake of completeness I have reintroduced it, that this is how you write the likelihood function. You have a population density function which is given by f of x theta, and if you have a sample from x1 to xn, then you take the product of f of x1 theta, f of x2 theta up to f of xn theta, and this is what you get. Right, now the question is that since we are trying to talk about method of maximum likelihood, so our aim is to maximize the likelihood function L. So how to maximize the likelihood function L? To maximize, we have to take del L by del theta is equal to 0, and we have to take del 2 L by del theta squared less than 0. But since L is a likelihood function, and here you can see that we have product of different terms, so to simplify it, it is always better to take the log. Why it is better to take the log? Because if we are trying to maximize L, and log L is also a non-decreasing function of L. Right, so for increasing value of L, log L will also increase. So if we can maximize log L, then certainly L will also be maximized. So in spite of taking del L by del theta, I will be taking del by del theta of log L, and this is being done to maximize the likelihood function L. And why we are trying to maximize the likelihood function L? Because we want to get an estimator to estimate the parameter theta. So to make sense of all of this, let us take this problem, and this is one of the important problems. So listen it very carefully. Then through this you will be able to understand the process also. So this is the first out of the three problems that I am going to discuss. So in a sampling from normal mu sigma square, find the maximum likelihood estimator of mu when sigma square is known. Second part is sigma square when mu is known, and third part is simultaneous estimation of mu and sigma square. So it is given that x follows the normal distribution with parameters mu and sigma square. So first of all, we have to write the likelihood function. So how the likelihood function is written? We take the product of I varies from 1 to n, and then we write the probability density function. So for a normal distribution, I hope you remember the probability density function is given by 1 by sigma under root 2 pi. You have to remember this because this is a standard distribution, e to the power minus 1 by 2 sigma square into xi minus mu whole square. Right. So I have to take the product of it. So to take the product of it, this term, that is 1 by sigma under root 2 pi, this will come with each of the term, like for I is equal to 1, for I is equal to 2, for I is equal to n. So if we multiply it n times, I will get 1 by sigma under root 2 pi whole to the power n, and e to the power this term, like x1 minus mu whole square into e to the power this x2 minus mu whole square. So if you multiply them, the powers will be added, and if the powers will be added, what I will get? I will get minus 1 by 2 sigma square, that is constant, and summation xi minus mu whole square, where I varies from 1 to n. I hope there is no doubt in this. Now since we want to maximize L, we have to differentiate L partially with respect to either mu or sigma square, depending upon what do you want to estimate. So what I told earlier, that it is always better to take the log of the likelihood function, because if you take the log of the likelihood function, this product terms becomes the sum terms. So I take log in both sides. So if I take log L, what it will become? It will become log L is equal to log of this term. So I write n log of 1 by sigma under root 2 pi, and minus, if I take the log of e to the power this, then log of e will become 1. So I will get minus 1 by 2 sigma square summation xi minus mu whole square, I varies from 1 to n. But I can rewrite this term again. So to rewrite, I write log of L is equal to, and be very careful that what I am going to do, because you may be this may be slightly confusing. So let me write it here, otherwise you will not be able to understand. So I am going to focus on this term. So we have the term like n, and log 1 by sigma under root 2 pi can be written as log of 1 minus log of sigma under root 2 pi. Okay, log of 1 we know is equal to 0, so I will get minus n, and this can be written as log of sigma under root 2 pi can be written as log of sigma plus log of under root 2 pi. So this I can write minus n log of sigma and minus n by 2 log of under root, not under root, because I already have taken this 2 pi to the power 1 by 2 in the beginning of log. So I will write 2 pi, right? I hope you got this. This is 2 pi to the power 1 by 2. Now one thing, that sigma is not our parameter. Our parameter is sigma square. So I hope you will not hesitate to write this, that it is minus n by 2 log of sigma square. Both of them are same thing, because if you take 2 in the beginning of log using the property of log, 2 and 2 will cancel, so I will get the same thing, and then minus n by 2 log of 2 pi. So I am writing directly here so that you don't get confused. So I hope you have understood it. So this can be written as minus n by 2 log of sigma square minus n by 2 log of 2 pi, and then minus 1 by 2 sigma square summation xi minus mu whole square, I varies from 1 to n. And this is our main result, because I will have to maximize log L. So there are three parts of the problem. So I'm going to discuss them case by case. So let us talk about the case 1. Case 1 is when sigma square is known, and we want to find the estimator for mu. So what we have to do, I want to find the estimator for mu, so I have to differentiate log L partially with respect to mu. So I am going to write, this is known as the likelihood equation. So del by del mu of log L, that I have to put equal to 0. This is what I have shown you here, that if you want to estimate theta, you have to differentiate log L with respect to theta. So here I want to estimate mu because sigma square is known, so I have to differentiate log L with respect to mu, and I have to equate that to 0. But if you differentiate this with respect to mu, I want you to look at this carefully because I have to write it in the next page. I am differentiating it partially. There is no mu term in the first, so this is a constant in with respect to mu. So if you differentiate this term, it will give you 0. And if you differentiate this term, this is of course a constant term, so this will give you 0. And you have to differentiate this term. So from I will get minus 1 by 2 sigma square, right? So I am writing it here. So I will get minus 1 by 2 sigma square, right? And then I have to differentiate xi minus mu whole square. So I write it summation I varies from 1 to n and xi minus mu whole square. So this will give me 2 times xi minus mu. So I am writing 2 times xi minus mu. But since we are differentiating it partially with respect to mu, I have to differentiate mu again. So this is a minus mu, so I have to multiply it by minus 1, and this I have to equate equal to 0. I hope it has made sense to you, because I repeat it, if I have to differentiate this part, it will give me 2 times xi minus mu, and here the coefficient of mu is minus 1, so I have written minus 1 here. Now let us focus on this term now. So minus 1 by 2 sigma square can't be 0, so certainly this term, this term here should be equal to 0. So I write summation I varies from 1 to n, and this minus 2 can be taken out again. Xi minus mu should be equal to 0, because if the product is 0, this thing cannot be 0, minus 1 by 2 sigma square. So again I can write, just to simplify it, that I varies from 1 to n, minus 2 is there, so I will not write xi minus mu is equal to 0, because if this term is 0, certainly this thing should be 0, minus 2 is not 0. Now if you look at this term, this is basically what? This is basically x1 minus mu plus x2 minus mu. If you allow me, I can write this for you. So this is x1 minus mu plus x2 minus mu up to what? Up to xn minus mu, right? So you can see that here you will get x1 plus x2 up to xn, the first term, and minus mu minus mu minus mu. So if you take it in the right hand side, you will get n mu. So what you are getting? You are getting basically mu is equal to 1 by n, and this whole thing can be written as summation of xi, I varies from 1 to n. So we got what? We got mu is equal to x bar, right? So because this thing is nothing but x bar, so we can conclude now that what is the maximum likelihood estimator of mu. So we write that maximum likelihood estimator, that is MLE, for mu is the sample mean. What is x bar? X bar is the mean of the sample that you have taken, that is the sample mean x bar. And this thing we already have highlighted also, that maximum likelihood estimator in case of a normal population is the sample mean, that is x bar. Now we have to do the next part. So what is the next part? Next part is that we have to case 2, we have to estimate sigma square when mu is known. So let us do one thing. For our convenience, I am going to write the log L expression on this, so that we don't have to go again back and forth. So let me write log L expression here. So this is our log L expression. Now the case 2 is that we have to find sigma square when mu is known. So what we have to do now, we have to estimate sigma square. So I am going to write the likelihood equation, that is del by del sigma square and I am going to differentiate log L. So I am differentiating it with respect to sigma square, and that I have to put is equal to 0. Now if I have to differentiate it with respect to sigma square, you can see that you have a term of log sigma square here, and now you might have realized that why I have written sigma square earlier. So if I differentiate log sigma square with respect to sigma square, you know that the derivative of log x is equal to 1 by x. So the derivative of log sigma square with respect to sigma square will be 1 by sigma square. Okay, and what will be the next thing that I will be getting? The next thing that I will be getting is equal to here minus, if you differentiate this term, this summation term does not have any sigma square, and here we have minus 1 by 2, and if I differentiate 1 by sigma square, I will get minus 1 by sigma square square, that is sigma to the power 4, and then I will get summation xi minus mu whole square. I varies from 1 to n. Some students get confused with this. I hope you are getting. I am differentiating del by del sigma square of 1 by sigma square. So do you remember this result? The result is d by dx of 1 by x is minus 1 by x square. So I am differentiating 1 by sigma square with respect to sigma square, so that will be minus 1 by sigma square square, so that will be minus 1 by sigma to the power 4. Now I have to simplify this expression, and this is equal to what? This is equal to 0. So if I simplify this, this minus and minus will become plus, so I will get 1 by 2 sigma to the power 4 summation xi minus mu whole square. I varies from 1 to n, and if I take it in the right hand side, I will get n by 2 sigma square. Now I need to cancel some of the common terms. So 2 is there, 2 is there, and here we have sigma square, and here we have sigma to the power 4. So what I can write? I am writing, if I take sigma square in the right hand side and n in the left hand side, I will get sigma square. So sigma to the power 4 by sigma square will become sigma square, and if I take n in this side, I will get 1 by n summation I varies from 1 to n xi minus mu whole square. Now for mu we already have kind of calculated the estimation. So what will I get in this case? So just for our convenience, I can write that sigma square is equal to 1 by n and summation I varies from 1 to n xi minus, what is the maximum likelihood estimation of mu? That is x bar. So xi minus x bar. So this is the maximum likelihood estimator for the parameter sigma square. So we have discussed both the cases, that is mu when sigma square is known and sigma square when mu is known. And we have the third part when we have to estimate both mu and sigma square. So this is not something that I have to separately do. We already have done the calculation. So for simultaneous estimation, what we have to do? We have to write both the equations like del by del mu of log L is equal to 0 and del by del sigma square of log L is equal to 0. So this I already have solved as case 1, and this I already have solved as case 2. So this will give me mu is equal to x bar, which you already have seen, and this will give you sigma square is equal to 1 by n summation xi minus x bar whole square. So this is the simultaneous estimation of mu and sigma square. You don't have to do it separately. You can write that using case 1 and 2 we have. So you can write here using case 1 and 2 we have this. So this is how the maximum likelihood estimation problems are done. Well, so this is the next problem. So we have to prove that the maximum likelihood estimate of a parameter alpha of a population having density function, this for a sample of unit size, and this is important here, the sample is of unit size, means we are just taking one value, is 2x. So we have to prove that the maximum likelihood estimate for this will be equal to 2x, where x being the sample value. And the next part we have to show that estimate is biased. So how to do that? First of all, we have to write the likelihood function. So here we want to estimate alpha, so the likelihood function will be written as a function of alpha, and we take the product of probability density function, but here we have just one sample value, so I will just write 2 by alpha square into alpha minus x. Right, you have just one value, so certainly you can't take the product. Now usually I should write vertically, but just to save a space I am writing like this. So I am taking log in both sides, so log L will be equal to what? Log L will be equal to log of 2 plus log of alpha minus x minus 2 log alpha. And the likelihood equation, so the likelihood equation is we want to estimate alpha, so del by del alpha of log L is equal to 0. So this will give me what? I have to differentiate this. So if I differentiate this, log 2 will be equal to 0, derivative of that. This will give me 1 by alpha minus x, and this will give me minus 2 by alpha is equal to 0. So I have to simplify this. So 1 by alpha minus x will be equal to 2 by alpha. So this will give you what? This will give you alpha is equal to 2 alpha minus 2x. So you can take 2x in the other side, alpha in the other side, so you will get alpha is equal to 2x. So this is what they wanted me to prove, that maximum likelihood estimator of a parameter alpha of a population having density function, this is given to be 2x. So I have got alpha is equal to 2x. Now the next part we have to prove that 2x that estimator that I am using is a biased estimator. So for that, what we have to prove? We have to prove that if I take the expectation of t, it should be equal to theta. So the t that is defined here is given by 2 of x. So to show that it is a biased estimator, what we have to show? We have to show that expectation of 2x is equal to, if I can show expectation of 2x is equal to alpha, then it will be a unbiased estimator. So it means what? That somehow I have to show that expectation of 2x is not equal to alpha. So how do you find the expectation of 2x? Do you remember? It is a continuous probability density. So to find the expectation of 2x, you take 2x into the probability density function, that is 2 by alpha square into alpha minus x dx, and you have to integrate it between the limit that is 0 to alpha. So if I do that, here I have 2 into 2, 4 by alpha square, that is constant, and here I have to integrate 0 to alpha, and what I will have here, we have alpha into x minus x square dx, right? So this will give me, ladies and gentlemen, 4 by alpha square, and alpha x will give me alpha x square by 2, and x square will give me x cube by 3. Limit of integration is 0 to alpha. So I got 4 by alpha square. I put the upper limit, so alpha square into alpha will give me alpha cube by 2, and if I put here, I will get alpha cube by 3, and if I put 0 in place of x, both the terms will become 0. So I am getting this is equal to 4 by alpha square into it will be like alpha cube by 6. I hope you got it. 3 alpha cube minus 2 alpha cube by 6. So you will get what? You will get 4 by 6, that is 2 by 3, and alpha cube by alpha square, that is 2 by 3 alpha. What was my aim? That if this is an unbiased estimator of alpha, then it should be equal to alpha, but what we are getting is 2 by 3 alpha, which is not equal to alpha. So it means what? That alpha is equal to 2x is not an unbiased estimator, right? It is not an unbiased estimator, because if I am taking the expectation of 2x, I am not getting alpha, I am getting 2 by 3 alpha. So this is how we can do the other problem. Now let us move to the third problem, right? Because this is also an interesting one. So the third problem is that find the maximum likelihood estimate for the parameter lambda of Poisson distribution on the basis of a sample of size n, right? So I will not delay this, I will just quickly solve it. First of all, do you remember that what is the probability density function of a normal distribution? It is given by f of x lambda is given to be e to the power minus lambda to the power x by factorial x, where this x can take values from 0 to infinity. This is a discrete probability distribution. This we know. So we have a sample of size n, right? So it is given in the problem that find the maximum likelihood estimate for the parameter lambda of Poisson distribution on the basis of a sample of size n. So let us take that let x1 comma x2 comma xn be a sample of size n. So first step we have to write L. L is product of I varies from 1 to n f of xi lambda, right? And here L will be a function of lambda. So here product of I varies from 1 to n, and what is f of xi lambda? It will be e to the power minus lambda to the power xi by factorial xi. I hope you will be able to write this. If you take e to the power minus lambda will come n times, because for I is equal to 1, for I is equal to 2, for I is equal to n. And e to the power minus lambda, if you multiply n times, the exponents will be added. So minus lambda will be added n times, so it will become e to the power minus n lambda and into lambda to the power. So the first power will be x1 if I take I is equal to 1, second power will be x2, third power will be x3, last power will be xn. So it will become summation of xi, I varies from 1 to n, and divided by, here I will get what? Here I will get factorial x1 into factorial x2 dot 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 up to factorial xn. So this is my L. So what we will get if I take log in both sides. So if I take log in both sides, log of e to the power minus n lambda, so I will get minus n lambda, plus log of this term, so I will get summation xi, I varies from 1 to n, and log of lambda, and minus log of, in the bracket I write factorial x1 into factorial x2 up to factorial xn. Now this is my log L. So what is the likelihood equation? So the likelihood equation is del by del lambda, because I want to estimate lambda, of log L should be equal to 0. So now I differentiate this. So if I differentiate this, minus n lambda, so I will get minus n, plus if I differentiate this term, here we have log lambda, so I will get 1 by lambda, and this will be a constant, so it will be summation xi, I varies from 1 to n. I think it would have been better if I write it later, otherwise some of you may get confused that what I have done. So let me write this later, because if I differentiate this, this will be a constant, and so I have taken it outside, and differentiation of log lambda will be 1 by lambda, and minus, if you take this term, there is no lambda term, so it will all become 0. So that thing should be equal to 0. So what did I get here? I got, if I take this n in the right hand side, I will get summation xi, I varies from 1 to n, into 1 by lambda is equal to n. So from this I will write what? I want to write lambda. So lambda will be equal to 1 by n into summation xi, I varies from 1 to n. So lambda I have taken in the other side, n in this side. So now this thing that you have got, the last term that you have got is what? 1 by n and summation of xi. So basically you have got lambda is equal to x bar, right? So the maximum likelihood estimate for parameter lambda on a sample of size n is equal to x bar. So here also you can see that sample mean that is x bar is the maximum likelihood estimate of lambda, that is the population parameter. Okay, so this is the third problem, but before I complete this video, I want to discuss the properties of maximum likelihood estimate, and these are very important because in exam sometimes they may ask MCQ based on this. So the first property is that I already have talked about, that maximum likelihood are always consistent estimator. So whenever you are calculating the maximum likelihood estimator, they are always consistent, but here it is written not it is not nut, it is but need not unbiased. So maximum likelihood estimator are not necessarily unbiased. You have seen in the problem also, this problem I have proved that this was not unbiased. So they may ask you this question also, that whether maximum likelihood estimator are always unbiased. No, it may not necessarily be unbiased. For example, if you talk about a normal mu sigma square population, the sample mean, that is x bar, is unbiased and consistent estimator of mu, but the sample variance s square is consistent but not unbiased estimator of sigma square. In case if you have watched the first video in estimation theory series, I have even proved it, that when we calculate when we have to estimate sigma square, we don't take the sample variance like s square is equal to 1 by n summation xi minus x bar square, because this is a biased estimator. What we do, we take 1 by n minus 1 summation xi minus x bar square. This is an unbiased estimator that I have proved earlier. Second property, if maximum likelihood exists, it is the most efficient in the class of such estimators. So maximum likelihood estimators are the most efficient estimator. Third property, if a sufficient estimator exists, it is a function of the maximum likelihood estimator. So sufficient estimators are what? It is a function of the maximum likelihood estimator. These results can be proved also, but it will go beyond the scope of our discussion. And the last property is known as invariance property of maximum likelihood estimate. So what is that invariance property? That if t is the maximum likelihood estimate of theta and psi theta is 1-to-1 function of theta, then psi t is the maximum likelihood estimate of psi theta. We have seen the invariance property in case of sufficient estimator and invariance property in case of consistent estimator. So if I am talking about maximum likelihood estimator, if t is the maximum likelihood estimator of theta, right, and psi t and psi theta is 1-to-1 function of theta, then what will be the maximum likelihood estimate of psi theta? Maximum likelihood estimate of sin theta will be psi t. Right, so this is the invariance property. So with this we complete the topic of maximum likelihood estimate. I have discussed 3 problems. I hope you have understood it. Try to write the problems at least once, so that you do have the sufficient confidence. And I would also suggest you that from the book or wherever you can get the problem, try to solve more problems on maximum likelihood estimate, because this is a very important topic, usually asked in the exam as well. So that's all for this video. Thanks for watching. In the next video I'll be talking about the central limit theorem. Okay, that's all. Have a nice day.